Well, there's a certain amount of energy then that is required for one of these molecules to break all of these attractions and to escape into the gas phase, right? So it escapes out here and becomes a gaseous molecule. Now, it doesn't have to quote unquote boil to do that, because for example, if you were to go outside, let's say, let's say, you pour out some water out there, then on the ground or right here on the desk, and you come back tomorrow, the water will all be gone. And it didn't boil outside. It wasn't 100 degrees outside. It was just evaporation. Well, why does that happen? Because over time, these molecules, some are going a little faster, some are going a little slower. And if some of the ones then that are going a little bit faster and have some more kinetic energy, if they happen to reach the top, well, they'll have enough energy then to actually break free into the gas phase. But again, like I said, there's only a certain small fraction have that amount of energy. Well, whatever fraction at that temperature are able to escape, well, they're going to create a few little gas particles up here. Okay, well, those gas particles are going to create a certain pressure, right? Because as they're bouncing around, they're going to bounce around off the walls and create a certain pressure. That's what's called the vapor pressure. So the vapor pressure is that thing I was just showing you on the little slide here. So that is the vapor then that's being collected above the liquid in a closed container. So those few molecules then that are escaping and they're bouncing off the walls and the cap and whatever, they're going to create a certain pressure. Okay? So every liquid is going to have a different vapor pressure because they each have different kinds of forces holding them in the liquid phase. Well, some then are going to have weaker forces, which means it's easier then for those to escape into the gas phase, and they'll have a higher vapor pressure. And some will have stronger forces holding them in the liquid, and they would have a lower vapor pressure. But that will change with temperature. Okay? Because you warm up water, let's say from like 20 degrees to 30 degrees to 40 degrees. Well, now on average, more of them have a higher energy. There's going to be a few more of them that are able to escape and create that pressure. So the question is, well, why do things boil? Why does it boil then at 100 degrees? What's special about 100 degrees? Well, at 100 degrees, that is the case where the natural vapor pressure, or the natural pressure then of the gases that are then escaping into the atmosphere, when that pressure is the same as the pressure around it in the air, well, then now there's no kind of barrier, and it's just a free-for-all, and they are freely able then to leave the liquid and go into the gas. So basically, things boil when their vapor pressure, the pressure of the gas naturally escaping, is the same as the pressure of the air around it. That's when things boil. And for water, that happens to be at 100 degrees Celsius. Because at 100 degrees Celsius, the natural vapor pressure of the water is about 1 atmosphere, which is the same as the air around it. So that's when they start to boil. So I have a little chart here I'll show you. And this kind of shows water vapor pressure at different temperatures. So let's say, for example, at around room temperature, roughly 20, 25. Okay, so at 20 degrees, well, what's the pressure of the water then that's naturally escaping into the gas phase? Well, it's only about 18 millimeters mercury. But you see, as you warm it up, well, now you have more and more gas being able to escape, creating a larger pressure, until you finally get down to 100. We're now at 760, which again is about 1 atmosphere, about standard pressure. Okay, so that's when things boil, is when that pressure of the gas naturally escaping is the same as the pressure of the room around it. Okay, so now I want to wrap back up here and look at, depends on, I should mention it's going to be lower at higher altitudes. It's 2. So why would things boil, let's say, at 95 degrees when you're a mile up instead of at 100 degrees? Why do things boil lower?
Lower pressure.
Because it's lower pressure in the air around them, right? So there's less pressure as you go up higher and higher. So let's say you're a mile up and the pressure is 634 in the air. Well, now your gas or your water will boil at 95 degrees instead of 100 degrees, right? So it just boils a little easier. Which is why, sometimes when you read on the directions, it'll say for higher altitude cooking, cook it a little longer. because now you're only cooking it at 95, not at 100, so you have to cook it a little longer. It'll say things like that, on there. Okay, well, let's go back and kind of review what we did last time, and then we'll tie those all together. So we looked at Boyle's Law, named for Sir Robert Boyle, back in the 1600s. That was P1 V1 equals P2 V2. So the initial pressure times the volume is the same as the pressure times the volume after you change one of the two. Then we had Charles's law. What was Charles's law? What was that one? Pardon me? V1 over T1 equals V2 over T2. Okay, right, good. And then we had another French guy, Gay-Lussac's law. And what was his? P1 over T1 equals P2 over T2. Okay, well, so now we're going to do is we're going to take those laws, we're going to combine them all, and then we'll have a law that will handle all three, pressure, volume, and temperature at once, not just two of the three. So you can kind of see, it looks like the pressure and the volume are both on top, right? And the temperatures are on the bottom. If you were to work it all out, you would wind up writing something like this. So this is called the combined gas law. Maybe I should write that over here. Let's write over here, combined gas law. P1V1 still, but now over T1 equals P2V2 over T2. So this is called the combined gas law. So this one now allows us to change not just two variables, but we can change all three. So we could change the pressure of the balloon plus the temperature of the balloon and make the balloon bigger, change the volume. We could do all three, and we can see how it's going to respond. So you can see then now out of this combined law how all the other laws are basically wrapped up in here. So let's look, for example, at Boyle's law. So Boyle's law then, we're not considering temperature. We only worry about pressure and volume. Well, in that case, if I ignore temperature, you see I have Boyle's law right there, right? Charles's law ignores pressure. Well, if I ignore pressure, can you see I have V over T equals V over T? Now I have Charles's law. And Gay-Lussac's law ignores volume, so there I have Gay-Lussac's law in there too. Can you see? So yeah, they're all kind of wrapped up in that one handy law. Okay, kind of nice. So that is our new friend, the combined gas law. P1 V1 over T1 equals P2 V2 over T2. Okay, well, let's look at an example problem here. If you have your handout, go ahead and pull it out. We'll just do the first one on the handout together. Oh, I skipped it. Let's go back. If you have 2.9 liters of a gas at a pressure of 5.0 atmospheres and a temperature of 50 degrees Celsius, so that's what your initial conditions were. What will be the temperature of the gas after you decrease the volume to 2.4 liters and decrease the pressure to 3.0 atmospheres? So now you can see we have all three variables changing: pressure, volume, and temperature. Okay, well, let's look here. So combined gas law, P1 V1 over T1 equals P2 V2 over T2. Which variable do I want to solve for in this equation? Okay, I want to find the new volume after I change the new temperature after I change the volume and pressure. So T2. So I have to isolate this one down here, right? So, but we learned last time how to cross multiply, right? So you can move this up here and then move these down here and these over here and squish things all around. And if you have any questions on that, please come see me. Ask me during lab or something. I'll be happy to give you a little refresher there. So you should get something like that. Is that what you got? So, right, so we're going to move the T1 up here. So the P1 V1 down here and the T2 over by itself. Okay, now we're going to plug in and see what we know. So tell you what, let's go back and let's label things in the equation. Sometimes it helps out with word problems. So 2.9 liters, which variable is that one?
V1.
That is the initial volume, V1, right. 5.0 atmospheres, what's that? P what? Yeah, the initial pressure, right? 50 degrees Celsius, what's that? T1, good. Okay, decrease it to 2.4 liters, what's that? V2, right? And 3.0 atmospheres? Okay, good. So now you kind of know where to pull from and what to plug in there. So, okay, let's look here. So, P2 we said was 3.0 atmospheres. V2, 2.4 liters. T1, 50 Celsius, but you know, whenever you have a gas, you gotta put it into Kelvin. Do not forget that. You must put it into Kelvin. So let's do that real quick. 50 plus 273, 323 Kelvin. 323 Kelvin. P1 we said was 5.0 atmospheres, and V1 2.9 liters. So which units cancel out when I do this? Yeah, atmospheres cancel out, and what else? Liters cancel out. So what unit am I left with? Kelvin. Kelvin, which is what I want because I want a temperature. So punch that in your calculator. What'd you get?
160 Kelvin.
160 Kelvin. Anybody else?
Yeah.
Okay, there you go. Okay, and again, like I mentioned on test or quiz, I will give you the equation. You just have to know how to rearrange it. And you got to remember to convert Celsius to Kelvin. Don't forget that. Convert that Celsius to Kelvin every time. Okay, why don't you try this one? An unknown volume of a gas has a pressure of 365 millimeters of mercury and a temperature of 325. If the pressure is raised to 1.2 atmospheres, the temperature is decreased to 320 Kelvin, and the final volume measures 4.8 times 10 to the third milliliters. What was the initial volume of the gas in liters? So we definitely have some converting to do. Do you see that? So tell me what you're going to have to do converting on here. Okay, so let's go through the variables again. 365 millimeters mercury. Which variable is that? Pressure what?
P1.
That's P1. Okay. 325 Kelvin. What's that? T1. 1.2 atmospheres. What's that? P2. 320 Kelvin. T2. 4.8 times 10 to the third milliliters. So what am I solving for? Right, V1. So notice my two pressures. One is in millimeters mercury, one's in atmospheres. So your choice, either make them both millimeters mercury or make them both atmospheres. And then the volume, it wants the volume in liters. So you should probably turn that into liters before you plug it in. And you'll get out what you want. What's the conversion between atmospheres and millimeters mercury? Do you remember that one?
7.0.
1 ATM equals 760.
Right, exactly 760 millimeters mercury. And that has been defined, so that's exact. So yeah, Okay, well, do a little converting, plug it in, practice, see what you think. Help each other out if you need to. So rearrange your equation to solve for V1. You want to check that out with your neighbor and see if you both rearrange the equation the same way. And then, check your conversions and let's try it out. So P1 V1 over T1 equals P2 V2 over T2. Now you could just plug everything in as a number and then solve at the end for V1. I just always like to rearrange it first, but you don't have to do it that way. You could just put in P1, T1, P2, V2, T2, and then punch the numbers around later. But whatever works best for you. I just like to rearrange it all first. So P2 V2 T1 over T2 P1. So P2 we said was 1.2 atmospheres. V2 4.8 times 10 to the third milliliters. Well, okay, well, I'm going to go ahead and convert that. Or you could actually leave it, and then your answer will be in milliliters, and then convert it at the end. But I'll go ahead and convert it now. So I'm going to convert V2, 4.8 times 10 to the third milliliters, times 1 milliliter, 10 to the negative third liters. So that winds up being 4.8 liters, right? So 4.8 liters. T1 was 325 Kelvin. T2, right, we said right there, was 320 Kelvin. P1. Well, P1 is 365 millimeters mercury. And the other one's an atmosphere, so we'll be sure and convert that into atmospheres also. So P1, I'm going to take 365 millimeters of mercury and say, okay, 1 atmosphere is 760 millimeters of mercury. How many atmospheres does that give you? 0.48 what?
480.
Okay. So 0.480 atmospheres. So I will encourage you, as always, put in your units. Don't just put in numbers. Put in the actual units. Then you can make sure things are canceling the way they need to. Then you'll be sure which unit you're left with. So now I can see, oh, atmospheres, atmospheres. Kelvin, Kelvin. I'm left with liters, which is what I want, liters. So that seems like a good setup. And what'd you get, 12?
I got 12.2.
I think it was like 2 sig figs, though, because of the 1.2 atmospheres. So I'll say 12. How'd you do? Awesome. Okay. These aren't so bad. Let's try one more. Try another one here. Read it. You may want to go through, like I said, and label the variables first if that was helpful. Make sure both the pressures have the same units. Both the temperatures have the same units. Both the volumes have the same units. Try it out. 2.5 atmospheres. Well, let's see. Okay, so yeah, let's just do it the way I was just discussing here with Jamila. Sometimes that I like to do it is just write down every little variable and then fill in what I know. Sometimes that's a handy way to make sure I know. So I'm just going to put P1 equals V1 equals T1 equals. Sometimes this is helpful. Okay, let's fill in what we know. What is P1? Do we have a P1? That's what we're trying to find. So I'm going to put question mark. What's V1? 28 liters. What's T1?
318 Kelvin.
Okay, 45 Celsius, right? And we'll convert that here in a second. P2, 2.0 atmospheres, ATM, yes. V2,
34 liters.
T2.
3566.
Okay, so yes, we do need to convert those both into Kelvin, so add 273, makes that 318 Kelvin. 35 plus 273, 308 Kelvin. Okay, now let's do our equation. So P1 V1 over T1 equals P2 V2 over T2. The original pressure is going to be P1, right? So P2 V2 T1 over T2 V1. Now we just plug in everything we got over there on the left. So P2, 2.0 atmospheres. V2, 34 liters. T1, 318 Kelvin. T2, 308 Kelvin. And V1, 28 liters. So liters cancels, Kelvin cancels. I'm left with atmospheres. And how many atmospheres was it? 2.5 atmospheres. Sounds good? Okay. Awesome. Okay, so we have talked about pressure, volume, and temperature, but I told you there was a fourth factor, which was the amount of the gas that'll change it. And I said typically the variable for that's going to be N, which was what? Remember what N was, I said? N was the amount, but normally N was in what? Moles, yeah. And when you think of moles, we think of our buddy Avogadro. Avogadro's number, right? Number of particles in a mole. So Avogadro also worked with moles or amounts of gases as well. So Avogadro's law, again, you don't have to write down the first part if you want, but basically the whole end point that we're shooting for is Avogadro's law, V1 over N1 equals V2 over N2. So of course, as you would expect, as you have more moles of a gas, the volume is going to increase, right? So you blow more air into a balloon, it gets bigger. If you remove moles, it gets smaller. So they are proportional. Increase moles, increase volume. Decrease moles, decrease volume. Okay, so now we have Boyles, Charles, Gay-Lussac, and Avogadro. We got all of these people. Okay? So let's just try one or two here with Avogadro's law. So pull out your hand out there, and let's try a couple. So Avogadro's law is V1 over N1 equals V2 over N2. So it says 5 liters of a gas contains 0.965 moles. If the amount of the gas is increased to 1.80 moles, what will the new volume be? Assuming we don't change the temperature or the pressure, it says. So which variable do I want to solve for? V2, the new volume, V2. So V2 would become V1 times N2 over N1. Okay. So what's V1? Well, what was the initial volume? 5.00 liters. What was N2, the final moles? 1.80 moles. N1, the initial was 0.965 moles. Awesome. Moles cancels. We have about twice the moles, so I'm guessing we'll have about twice the volume. Well, what's the answer? 9.3 something. What'd you say? 3.2? 3.3? That makes sense. Said it roughly doubled the amount of gas. You're going to roughly double the volume. Okay. Okay, well that's moles. What if I gave it to you as mass? Well, you know what to do with mass. You just use the molar mass and turn those masses into moles and then plug it in. So try this one. Let's say you have a cylinder, has a movable piston, like in an engine or something, and it contains 2.00 grams of helium. So, says more helium was added into the cylinder and the volume was adjusted, but the pressure didn't change. How many grams of helium would you have to add to increase the cylinder from 2 liters to 2.7 liters? So, if you have 2.00 grams to start with, how many grams do you have to add to make it go from 2 liters to 2.7 liters? So this is a little bit of a thinker. Just think about it. What are you solving for? Feel free to discuss with the neighbor as always. Help each other out. Okay, well let's work this one out. So V1 over N1, oops, equals V2 over N2. We want to solve for N2. So we get V2 times N1 over V1. So V2 was 2.7, was it 0 liters? Was there a 0? I forget.
2.70.
Okay. N1, okay, well we don't know N1 yet. So N1 is moles, we had mass. Was it 2.00 grams, what it was?
Yeah.
Okay, so let's turn the mass of helium into moles of helium. So what's the molar mass of helium? 4 point what?
0.00.
Okay, so how many moles did that give you? Moles. .500 moles. Then the initial, I think, was 2.00, right? So, how many moles was it? 0.675 moles. Okay. But we want to know, put it back in grams. I'm going to turn it back into grams. So moles to mass, use molar mass again. So how many total grams did you get? 2.6 something, 70. What was it? 2.70. I can do that in my head. You're hurting my brain. So that is the total amount of helium you must have, but it doesn't want that. It wants how much helium was added to make it go from 2 to 2.7. Oh, well, we initially had 2.00 grams, right, initially? So we must have added 0.7 grams added. Does that make sense? Yeah. Okay, good job. That's funky how the masses and the liters were like the same. 2 grams was 2 liters. 2.7 grams was 2.7 liters. I just realized that. That's weird. Okay. Okay, good. So now we've seen pressure, volume, temperature, and moles, right? We've seen them all. So we can combine all of these. Don't write this down right yet. But think about it, right? So volume is inversely proportional. I'm sorry, volume is proportional to 1 over pressure. Volume is proportional to temperature. Volume is proportional to moles. So you could put all these together. Tn over P. You get something like this. And then again, you can try to figure out, okay, well, exactly how are they proportional? What's the constant that relates volume to N over T? If you were to solve that out, we call that R is the constant that relates the two. So then you can do a whole little math derivation, and we get this thing right here. PV equals nRT. This is called the ideal gas law. Oh, what's going on here? Ideal gas law. So this is our next big equation we'll use for the next week or so here. PV equals nRT. Pressure times volume equals moles times this new gas constant, R, times T. And what is that gas constant? It's right there. 0.08206 liters times atmospheres over moles times Kelvin. So that's called the ideal gas constant, R. Whoops. So notice the units on R. Notice those units. Liters, volume, atmospheres, pressure, moles, Kelvin, temperature. So that has everything in there. It's got P, V, N, and T are all in there. So whenever you're going to use this equation, in order for your units to cancel out, well, whatever pressure you put in there for it to cancel has to be in atmospheres. Whatever volume you put in has to be in liters. Whatever amount you put in has to be in moles. Whatever temperature you put in has to be Kelvin. Else they're not going to cancel, right? So from now on, everything's going to have to be in liters, atmospheres, moles, and kelvins. So notice, now this case is not when you're changing from one pressure to another pressure. This is just considering, okay, let's say I have a single gas and I know the pressure, the volume, and the moles, and I want to find the temperature. Or I know the volume, the moles, temperature, and I want to find the pressure. So it's when you have a gas and you want to find one of the missing pieces, we use this called ideal gas law, PIV-NERD. Kind of like pervert, only a little different. PIV-NERD, the pervert. So let's look at PIV-NERD. PV equals nRT. How many moles of hydrogen gas would occupy 0.500 liters at 290 Kelvin and 1.3 atmospheres? Okay, well, let's write our equation. So PIV-NERD, oops, wrong pin there. So which one do I want to solve for? N. So N will be PV over RT. So let's plug in what we know. So what's P? Which of those is P? The one in atmosphere is right. Okay, sorry, this keeps on stopping and reconnecting, so I can't write anything. But yes, 1.3 atmospheres is the pressure. What would the volume be? V. 0.500 liters. Good. R, now that's the constant. It's always the one I just showed you. 0.08206 liters times atmospheres over moles times Kelvin. And then T is 290 Kelvin. Okay, let's go through here and make sure our units are canceling. So atmospheres, atmospheres. Liters and liters. Oh. Oh no, it's not actually saying anything now. Okay.
Earlier and it caught up.
I know, I don't know what's in that. It's doing it really bad today. Is the Wi-Fi having trouble? Because all through Wi-Fi. Okay. Well, I guess I'll do it on the board if I have to. Okay. So we'll go back here, old school. All right, well, what's going on? There's no messages, no. Normally it's saying, oh, reconnecting or something, but it's not doing anything. Okay, so let's just do it then. Confusion here. So PV equals nRT. Let me change colors here. PV equals nRT. So I want to solve for T. So to divide both sides by nR, so PV over nR. Now according to R, everything has to be in liters, atmospheres, moles, and Kelvin. So my pressure has to be in atmospheres, and it is 5.00 atmospheres. My volume has to be in liters. Aha, it's not. It's in milliliters. So let's convert that real quick. Okay, now it's in liters, 4.8 liters. In 1.9 moles. R, gas constant, 0.08206 liters times atmospheres over moles times Kelvin. So, always check your canceling. That's your little safety net there. Atmospheres, atmospheres, liters, liters, moles, moles, left with Kelvin, which I should be because it's a temperature. And what did you say, 150? Is that what you said?
Yeah.
Okay. Okay, good. Okay, this one here is a slightly different. You got to do a few more conversions on this one, so try it out. So I'll let you read it and figure it out. Yeah.
So the last problem, did you wait till the end to convert it to? Because if you waited till you got like 153,000 and then move
Kelvin?
yeah.
And then turn it.
Move decimal over 3 places and then.
I guess technically, but that doesn't really work with your units. Your units aren't canceling then.
Yeah.
So that's why it gets you in trouble. Because you milliliters and liters won't technically cancel out. Yeah. Probably don't want to do that. Bad habit to get into. Figure it out here. Remember, just said over here. H2. Don't forget. 1 to 7 diatomics. So what is the mass? So PV equals, oops, nRT. I'm going to solve for the mass, the amount. So we're going to solve for N. According to R, everything has to be in liters, atmospheres, moles, and Kelvin. My volume is in liters. My pressure, though, is not in atmospheres. And my temperature is not in Kelvin. So we've got to do a little bit of converting there. So pressure, 680.4 millimeters mercury. 1 atmosphere is exactly 760 millimeters mercury. So what's that? How many atmospheres? 0. Point what?
895.
Give me one more.
3.
Okay. Temperature has to be in Kelvin, but it's in Celsius, so negative 48.0. And I got some decimals, so I'm going to use some decimals on my Kelvin. So what's that give me? 225, yeah. Okay. So let's plug in here. So P 0.8953 atmospheres. V 72.6 liters. R, it's constant, it's always 0.08206 liters times atmospheres over moles times Kelvin, and temperature 225.2 Kelvin. So let's cancel our units. Atmospheres, liters, Kelvin, Kelvin. We're left with moles. Perfect. Okay. So how many moles did you get? 3.52 moles. Okay. Okay, so what you got for moles, but it says it wants mass, so turn it to mass. So the molar mass of H2, 1 mole of H2, is 2.02 grams, right? So yeah, it's like 7 something. What is it? 7.11? Something like that. 1112, whatever. Okay, but
Is the hydrogen just not hydrogen gas? Would it have been 1.01 or would it have not?
no, it's hydrogen. It's just hydrogen by itself. Whenever it's not in the compound, whenever it's just by itself, not in the compound. Hydrogen and those other 6: nitrogen, oxygen, fluorine, chlorine, bromine, iodine. Okay, we've got 4 minutes. I think we can sneak out one more here. So let's sneak out the last one here. Then we'll be done with this little section. Start something fresh on Thursday. So same thing. Volume, milliliters. The amount is in grams. Temperature is in Celsius. What's the pressure? So solving for pressure. P. What's the pressure? Do it real quick. PV equals nRT. Which variable do you want to solve for? P, of course. So nRT over V. N is going to be moles. Well, I don't have moles, I have mass. But you know how to turn, grams into moles. Use molar mass. We add up 3 carbons, 8 hydrogens, right? So you do all that. What's that? 36, 8, 44.11. Okay, how many moles is that? 0.052. Should have one more sig fig technically because there was 3. Run out of room there, aren't I? 0.0521. Okay, good. So that's my N. 0.0521 moles. R is a constant. It's always 0.08206. You'll be given that, of course. You just got to know where to use it. Temperature has to be in Kelvin, so take your 23 and add 273. So 296. Then V, volume. Ours is in milliliters. 250 point. Notice the point makes it 3 sig figs. So turn that into liters. So 0.250 liters. 0.250 liters. So make sure everything cancels. Let's see. Moles, moles, liters, liters, Kelvin, Kelvin. We're left with atmospheres, which we should be, because it's a pressure. And what was it? Awesome. Good job. I think you guys did a good job on that today. Good. Okay, so my encouragement is always, what somewhat makes sense in your brain, you need to go reinforce it and do some homework. Do not wait a week and a half till it's due. I'll be like, how was I doing that? So do it now. Do it now, tonight or tomorrow. And if you have questions, come see me. Go to the tutor. But don't wait a week to practice this. So, okay, so we'll start a few minutes later. Since we're getting out 4 minutes later, we'll start 4 minutes later. So see you 10 minutes from now then.